So in the lessons leading up to this one on fun theorems, we learned about something called a definite integral. Definite integral turned out to be a limit of a Riemann sum, Riemann sum being a sum of products, and we use those things to find the area underneath the curve. We definitely came to the conclusion that those problems were an absolute headache. Think of this lesson here on fun theorems as the acetaminophen for that headache. You're going to see that after we learn about these fundamental theorems of calculus, it's going to really speed up that process and make it I'm going to say relatively pain-free. So we have two objectives. First one, find the derivative of something called an accumulation function using FTC1. That means the first fundamental theorem of calculus. And then we also want to evaluate a definite integral using the second fundamental theorem of calculus, FTC2. That's the one that's going to really help us with those limits of Riemann sum, the definite integral part of this. All right, to get us started on this process here, we're going to look at this warm-up question. And we have the let f of t equal negative 2t, and we're going to use a geometric formula to evaluate each of the following definite integrals. Remember that definite integral, we're interpreting this as some kind of area bound by the curve and the x-axis, or in this case, the t-axis. And I'm going to assume that most of you came into this video with this already completed, like you already know what the answers are, and you're only here to check to see if you got the right answers. So let's check to see if you did. All right, I'm going to go over these with you step by step, and if you do, I mean, you're more than welcome. You're more than welcome to play this on 32 speed times 32 speed if you want to. Really speed up the process of finding each one of these things. All right, let's look at the first one. We've got the definite integral from negative 3 to negative 3, negative 3 to negative 3 of f of t, this function here, negative 2t, with respect to t. Hey, didn't we learn this nice, neat little property that if you go from this bound to negative 3 to the same exact bound to negative 3, you get a whole lot of no area, right? That makes sense. If I start here on my graph at negative 3, and I come up to my graph, I think it should hit here at 6, and then I want to find the area from negative 3 to, nope, don't move. I get no area, right? I just get this kind of segment thingy that's right there. I don't have area. Nothing. All right, and let's move on to the second one. We want to find the definite integral from negative 3 to negative 2 of that function. This one should have some sort of area because we are actually moving off of our starting point. Here, let's draw it in here. I think that should hit at 4, because if we stick in a negative 2 into our negative 2t function, I should get positive 4. So here, this one is 6, this one's 4. Notice that's not a 4. Now it's a 4. We do get a trapezoid. Trapezoid area formula, just in case you forgot, half base 1 plus base 2 times the height, where our two bases here are the two parallel sides and our height is 1. You can also think of this as the average of the two bases multiplied times the height. Well, what's the average between 6 and 4? That's 5 times the height of 1, you get a 5. That's equal to 5. All right, let's do the next one, shall we? From negative 3 to negative 1. So let me get rid of some of my drawing here so I can extend out my area. I'm going to go to negative 1. It should hit here at 2. And we have a new height also of 2. All right, I take the average of these two bases. I do believe I get 4. So 6 plus 2 is 8. Divided by 2 is 4. Times the height of 2 gives me an 8. Gives me an 8. So notice that what I'm doing is I'm kind of accumulating some area here, right? I'm getting a little bit more area each time as I sweep underneath this graph. One way to think of that. All right, and then the next one here is going from negative 3 to 0, bam, which just makes a triangle. Its base length is 3, its height is 6. Multiply those together, I get 18. Take half of it, I get 9. It accumulated just a little bit more area. Okay, on the next one, we're going from negative 3 to positive 1, and when I do, now I'm underneath the x-axis. And remember, anything that's underneath the x-axis, we're going to take away from whatever's up above the x-axis. Up above the x-axis, we had an area of 9. Now we have a triangle to the right of the origin. Its base length is 1. Its height is 2. Multiply that together, you get a 2. Divided by 2 is 1. This is actually a negative 1. So we're going to take the 9 that we had before and take 1 away from it. That area is 8. We just lost a little bit in 8. Did I put an equal sign here? Here, let's keep it consistent, shall we? Okay. All right, let's keep going. Get rid of this because we don't need it. And then we're going to go from -3 to +2. That should hit at 4. Now my base length is 2. That makes an 8. I take half of it as 4. 9 minus 4 gives me a 5. Hey, wait a minute. That matches up with this 5 and matches up with this 8. Oh, it probably does. It's probably just a coincidence. It means nothing. It means nothing. I bet it does. All right, let's get rid of it. Let's do the next one, which I believe goes from -3 to +3. Wait, come on. There we go. -3, +3. That should hit at 6. It's the same exact triangle as what's up above the x-axis here. This is a +9. This should be a -9. They should cancel each other out and get 0 equals 0. And now I just have one more for you. We're going from -3 to 4. So I'm going to leave the drawing as it is right now because all of that stuff cancels out. And now we're going to start accumulating more area, which is just going to be signed negative because it's down below the x-axis. Let's get rid of that so I can color this in real pretty. Okay, so our new bases are a 6 as from before, and the new one, if I stick in 4, 4 times a -2 makes this a -8 down here, so it's an 8, base length of 1. Average of those two bases, 7 times 1 gives me 7. But since it's down below the x-axis, our t-axis is actually -7. Okay. So you're probably wondering what the point of all of that was. Was it just so that we could practice our geometric formulas like triangles and trapezoids? No, it wasn't. There is a point to it, and it has something to do with one of these fundamental theorems of calculus, which are going to bridge a lot of what we did in the very first semester with derivatives, what we're doing currently with antiderivatives, and finding the area underneath the curve, which brings us to our objective picture here, which when you read the text here from Ann Copeland, it talks about undoing things, and the things that undo stuff in math, of course, we call inverses. And we're going to think of what we're doing with the fundamental theorems of calculus, at least one of them, as having to do with inverses.